Welcome back, MEC 1330 Fluid Power. We're stepping into Chapter 3 in your book, and we are going to go through hydraulic pumps, okay? And talk about all the different aspects of pumps and things like that. All right, if we take a look, this is what a basic hydraulic power unit looks like, okay? And then we can see where the pump is located. Generally connected to the prime mover, okay? And then the pump has the supply line connected to it because we're pumping, out of the tank and we're supplying everything else to and from the system using the pump to supply things, okay? So the basic operating principle that moves fluid through a pump is similar in all pumps, okay? And we're going to break it down into the different pump sizes, or not sizes, but the different pump types, and you can kind of see what a chamber looks like inside a pump, okay? Because one way is enlarging the volume of the chamber, which allows fluid to enter the pump, okay? And this is going to be common on all the different types of pumps that we're going to look like. And then we reduce the chamber volume to move the fluid to the system. Okay, so we're going to make the chamber bigger and then smaller as we are literally pumping fluid in and out of the system. Okay, we have inlet and discharge valves, or we call them ports. They control the fluid movement through the pump, all right? So there's an input and an output, essentially, to each pump. Okay, we're going to talk about briefly rotary pumps. Okay, the pumping action is produced by revolving components. Remember, rotary means rotational, or things going round and around and around. Okay, if we have something called a reciprocating pump, okay, the rotating motion of the pump input shaft is changed to reciprocating motion, which then causes or produces the pumping action, okay? So reciprocating, I want you to think about, going back and forth, and we're going to use it. There's a rotary motion, but that rotary motion controls pistons, all right, or cylinders that are going to extend and retract back and forth, okay? So the basic breakdown of a pump, all right, this can be, anything from a bicycle pump where you use by hand and you pump up and down and push, fluid into your bike tire or things like that. But we increase the size of the chamber, okay, that pulls all the fluid into the pump. And then when we push the handle back down, we move all the fluid out of the pump. Okay, we're going to look at the different valves and things that help, keep it from escaping or overfilling or doing those sort of things later on in some future chapters, okay? So with the basic pump, like I said, reducing it. So we can constantly pull on this lever and go back and forth and increase the chamber size, decrease the chamber size, increase the chamber size, decrease. And that's what you're doing. If you've ever seen one of those like old school kind of like red bicycle pumps where you're going up and down on the cylinder, that's essentially, what you were manually doing if you ever had to fill your bike tire with one of those. Okay, the maximum pressure developed in a hydraulic system is determined by a few things. One is resistance to fluid flow in the system. The other is the force the prime mover can exert, okay? The output flow of the hydraulic pump is determined by the volume of the pumping chamber, right? How big we can make that chamber when we're pumping. And the operating speed of the prime mover, right? We might have some sort of motor or something that's helping with a reciprocating pump or things along those lines. All right, so just like in electrical class, right? The path of least resistance is important. If there's no force or load on the cylinder, there's no pump pressure. So just make sure that we know that. In the bottom right-hand corner, that's the symbol for a pump, and you need to make sure you know that symbol. Okay, notice there's a triangle on it, and that triangle is filled in. When the triangle is filled in, that lets us know that it is hydraulics. If that triangle was not filled in, it would be a pneumatic pump. All right, so just so that we know how that works. So what's going to happen to cylinders A and B when power is applied to the pump? We have cylinder A. It has a 4-inch diameter with a load of 2,000 pounds, and cylinder B, okay, has an 8-inch diameter with a load of 4,000 pounds. Okay, remember, path of least resistance. So you need to think about, in this case, which cylinder has the least amount of resistance to it when we do this. All right, so we're going to do some calculations here. Same picture. So if you're trying to write stuff down from the slide, same thing here. All right, so we got to calculate the area. Remember, that's pi d squared over 4, and then we have to find the pressure. Pressure is force over area. So we're going to take 2,000 divided by 12.5 and roughly 159.2 psi. Next, let's do the same thing with cylinder B. We have our 8-inch diameter with a load of 4,000 pounds. We calculate the area, pi d squared divided by 4, and we get 50.27 cubic inches, or I'm sorry, not square inches, not cubic inches. All right, and then pressure is force over area, so we're going to take 4,000 divided by 50.27, and our PSI is 79.57. So, path of least resistance. We have cylinder A has pressure of 159.2, cylinder B has pressure of 79.57. Cylinder B is going to move first until it fully extends, and then cylinder A extends. Why? Less pressure on B, all right? Path of least resistance. It only has a pressure of 79.57, whereas cylinder A has a pressure of 159.2. So make sure that you're paying attention to this. Even though the first cylinder, all right, has a smaller load, it's a smaller cylinder. So the path of least resistance is going to go to cylinder B, all right, based on the pressure calculations that we just did, okay? So let's talk about what a pump's displacement is. It's the amount of volume the fluid is just discharged per cycle. So if we're extending or retracting a cylinder, and I'll show you this in class, okay? But if we're extending or retracting, it's how much fluid we can go out. Think about taking a syringe, all right, and you go over to some water and fill the syringe up as full as you can with water and then push it out. That's the amount of fluid, all right, that you're going to discharge each time you fill that syringe with water and squirt it out. Cycle is one revolution of the pump shaft, okay, in a circular type motion. So we talked a little bit about flow rate in chapter 2, all right. We're going to deem it here as theoretical flow rate, right? This isn't an ideal condition where we have nothing really impacting the system, all right? It's still, if we pay attention, we see the 231 and the 1,000. Remember, that has to do, the 231 has to do with cubic inches, and the 1,000 has to do with cubic liters, okay? So it's very, very important we remember those numbers, and I reiterated that in chapter 2, all right? But flow rate is going to be Vp times N divided by 231 for our imperial units, all right? And it's Vp times N divided by 1,000 for our metric, where Vp is our displacement divided by, or times our drive speed, our RPMs, okay, how fast it's rotating per minute, okay, divided by either 231 or 1,000. Okay, so let's do an example here. We have a pump. It has a displacement of 3 cubic inches per revolution and is driven at 1,800 RPMs. What's the theoretical flow rate? So literally we can calculate Q, right, just by plugging into the equation on the previous slide. 3 times 1,800 divided by 231. Okay, and then we got to pay attention to the units that cancel out here. Remember, flow rate is in gallons per minute. So we can see that inches cubed will cancel with inches cubed. Revolutions will cancel with revolutions, and then it ends up with gallons per minute because when we divide fractions, we multiply by the reciprocal, so it ends up being gallons divided by minutes. So our flow rate in this case is 23.4 gallons per minute, okay? You would do the same thing if we did a metric one. I just didn't do a metric example for you here. All right, so let's look at pump drive and pump torque. All right, so the prime mover supplies input power to the pump by driving the pump shaft at a rotational speed. Okay, the pressure on the pump resists that rotation. All right, so the prime mover has to generate enough torque to turn the shaft against the resistance. You know, think of you trying to, you know, there's a screw that's really tight, and you're trying to use a screwdriver to overcome that torque to loosen it. Okay, same kind of concept applies with pump. It's got to overcome the initial pressure before it kicks in and can rotate. So theoretical torque, okay, we're going to show here is T subscript T. So theoretical torque, all right, is going to be pressure times displacement divided by 2 pi. One thing to note here is units. Okay, displacement is always in volume, so we have to know that cubic centimeters per revolution to cubic meters per revolution. In 1 cubic meter, there is 1,000,000 cubic centimeters. So you're going to need to know that for some conversions later on doing some metric stuff. So we have a hydraulic pump with a displacement of 4 cubic inches per revolution is selected for a system that's going to operate at a maximum pressure of 5,000 psi. What is the required drive torque? And this is where we're calculating the theoretical torque here. All right, so we have everything in units that we need right now. Okay, so we can take 4 times 5,000 and divide it by 2 pi, and we end up getting 3,183 inch-pounds. Remember, inch-pounds is a force, and it is in our terms of our torque. All right, so that should everything should work out nicely there. Now, you might have to do something in foot-pounds or things like that as well. Okay. A hydraulic pump with a displacement of 30 cubic centimeters per revolution is selected for a system that's going to operate at a maximum pressure of 40,000 kPa. Don't forget there's a K on there, which adds 3 more zeros. All right, so it's really like 40 million PA, all right, or pascals. What's the required drive torque? All right, so make sure we have to convert this. And the metric is a little harder because we always have to convert everything generally. All right, because whatever you're going to buy, whatever parts and pieces are going to be in centimeters and millimeters. Most likely, you're not going to get something that's always in meters. Because remember, a meter's rather long. Okay, so you're going to always have to do some sort of conversion. Okay, so we got to convert that 30 cubic centimeters per revolution to cubic meters per revolution. Okay, so based on what I gave you a few slides ago, we have to know in 1 cubic meter, there's 1,000,000 cubic centimeters. So we have to take 30 and divide it by 1,000,000. Or we can just move the decimal 6 places to the left, okay? And that'll take care of business for us. So we get 0.00003 cubic meters per revolution. All right, so we've done our conversion. Now that we're in the right units, we can substitute into the theoretical torque equation, okay, where we have our pressure. Notice it's not 40,000, it's 40 million because of that K on the pascals there. Remember, pascals is the same as Newton meter squared. Okay, but we use Newton meter squared here to show that the units cancel and how everything works out. And we get 191 Newton meters. Okay, that's our theoretical torque. Doing this in metric. All right, so power, remember from, we even talked about this in chapter 2. All right, okay, horsepower is torque times speed divided by 63,025. And kilowatts, okay, torque times newtons divided by 9,550 if we are doing metric. Okay, so we're going to apply those equations here. We have an electric motor drives a pump at 1,500 RPM with a 300 inch-pound torque. Okay, what's the power input to this system? So when we're looking for power in this case, we're looking for horsepower. Okay, so we can literally substitute right into this equation here. So 300 times 1,500 divided by 63,025. Okay, we're going to get 7 horsepower. Okay, so that motor is providing 7 horsepower for this pump to drive at 1,500 RPMs. All right, so remember we got an electric motor that's attached to the pump. All right, and that pump speed, we have to have a certain speed generally. All right, we got to have that torque that overcomes it. So we need at least a 7 horsepower motor to run this. Most likely it's probably running off like a 10 horsepower motor. But that's what it's drawing is 7 horsepower. Okay? You would do the same thing with metric. Okay? Let's look at pump efficiency. Okay? We always look at efficiency. When we did electrical, we did duty cycles or, it's always output over input whenever we do this. All right? So we're going to use the Greek letter eta. So we're talking about volumetric efficiency. And when we're talking volume, remember we're talking flow rate, okay? Flow rate is a volume, whether we're talking, cubic inches, right? Or which is our gallons per minute, or we're talking cubic liters, all right? Or cubic meters, right, which is liters per minute, when we're doing this sort of thing. So eta efficiency, QA over QT. Okay, actual over theoretical. So QA is actual, QT is theoretical. So, right, remember, because we can calculate everything in theory, but nothing works exactly as it does in real life, theory there's no other factors when we're looking at stuff in theory. So just write these down, okay? So flow actual, right, is eta V times Vp times N divided by 231, okay? And then we have the other one, obviously the 1,000 for metric. So write those down real quick, and then we'll move forward and do an example here. A pump has a displacement of 3 cubic inches per revolution and a volumetric efficiency of 0.93. If it's driven at 1,300 RPM, what will its actual flow rate be? Okay? So we have the efficiency. So we have eta, we have its displacement, and we have its speed. Okay, so we have pretty much everything we need if we're looking for just the flow rate. So remember these problems. I can give you, a few of the variables and ask you to solve for any one of these. I could ask you to solve for speed or displacement or its efficiency using this equation here. It just depends on what's given to you. Okay? So in this case, we can literally substitute in everything that we need to. So it's going to be 0.93 times 3 times 1,300 and then divided by 231. All right, make sure you're keeping track of order of operations as you type these in your calculator. Sometimes if you don't type them in right, your calculator just kind of goes in order of how it gets stuff, not necessarily order of operation. So make sure if you're following along at home that you're typing things in and getting the same answers that I have up here. All right. So our actual flow rate here is 15.7 gallons per minute. Okay. If we want to talk about overall efficiency, okay, it's just like what we talk about with everything else. Output over input. Okay. How much horsepower are we getting out versus how much horsepower we're putting in? How much kilowatts we're getting out over how many kilowatts we're putting in. So make sure you write those down. Okay, let's do an example here. Pump has an overall efficiency of 0.88. A flow rate of 40 liters per minute is used in a system that has a maximum operating pressure of 20,000 kPa. Please remember there's a K there. You've got to add 3 more zeros, so it's 20 million pascals. Okay, what's the input power required? So metric, right? I didn't do my animations right, so this one's already showing up on the screen here. But we have P times Q divided by 60,000, right? So we got to take 20 million times 40 divided by 16,000. Okay, so that's our 13.33 kW. Okay, and that's our output power. Then we have to calculate the input power. Well, we can use the input power using the efficiency. Okay, so if we want to know what the input power is required to get out that 33.3 kW, right? And this is important when you do designs maybe later on in the future, because you know what you want out of a system and you know how efficient that system needs to be. And based on what you calculate, that's what you actually want to buy for the system to make sure at that efficiency it will do that output for you. So this is an important way to calculate the input power. We're going to take the output power and divide it by the efficiency. Okay, and we're going to get 15.14 kilowatts. Okay, so we need to buy, a motor here, okay, that has at least 15.14. So maybe, since we always oversize and things like that, probably like a 20 kW motor would easily handle this system for us. But see, sometimes it's how you have to work backwards when you're doing the design of things so that you know what to buy for the system to make it work. So that's why this is an important type problem here. Okay, let's get into the meat and potatoes of some pumps here, and we can break pumps down into a couple different things. Positive displacement or dynamic. Dynamic, obviously, always changing. We call those non-positive displacement pumps as well. Positive displacement pumps we can break into gear, fixed, and piston. Okay, and we can break those down even more. Okay, we're going to break each one of these down in the next few slides as we go through this, but you can kind of see gear. Okay, it's fixed, which means that's the chamber size. So when we're using a gear pump, we cannot make that chamber any bigger. It will always be fixed. If we use a vane pump, that chamber can be fixed or variable, and I'll show you how that works when we have vane pumps and things like that. Okay, piston. Okay, we're not talking about necessarily the chamber there. We're talking about radial or axial. Okay, so it just maybe depends on how many pistons we're using in order here to make something happen. okay, to make the pumping action work. Okay, so if we take a look at our hydraulic pumps, 3 basic characteristics. In displacement, their pumping motion, and their fluid delivery characteristics. Okay, so those are the basic 3 characteristics of any pump that we're going to talk about with hydraulics. Okay, so displacement pumps, okay, that relates how the output of the pump reacts to the system. So we're going to talk mainly about 2 kinds, positive and non-positive. Positive displacement pumps produce a constant output per cycle. That's the important piece. Nothing varies, whatever, you're getting a constant output all the time. Where a non-positive displacement pump has large internal clearances, and you may or may not get a constant output the entire time. Okay, there's going to be some varying, and you'll see why in the next couple of slides. I'm going to show you a picture of what the chamber looks like on these pumps. Okay, so remember, positive displacement pumps, constant output. Non-positive displacement pumps, we might have a varying output, all right, from it. So why do we have that? Well, it allows fluid slippage in the pump, or we have results varying in flow output as the system load varies, all right? So, we might be putting something on and off a conveyor. So that's going to change the load. So that's how our load can change. So if we take a look here, this is a positive displacement pump, all right? So we are going to put out, remember, a constant output flow. And I'll have some diagrams where you're going to actually see the positive displacement pump actually rotating and putting fluid in and kicking fluid out and doing that sort of thing. But, as it's rotating, it's taking that fluid around, it's adding a speed or velocity to that fluid, right, so that we can get a higher flow out if we want to using this pump. This is a non-positive displacement pump. Remember, this is not going to produce a constant output because notice the chamber can get larger or smaller. Okay, and as we're forcing fluid in, okay, there's going to be these little veins that can drop down, or not veins necessarily in this one, I'm sorry about that. We're going to get into veins in a little bit. But in this case, notice the chamber is going to have more fluid on it. It's not the exact amount of the impeller. Okay, so there's some invariance in there as it goes through. Okay, so pumping motions, basic pumping motions in hydraulic pumps are rotary. So gear pumps, okay, that's kind of the first one I showed. Okay, this is a gear pump right here. And you can clearly see the gears in the middle of the diagram. We have reciprocating pumps, okay? These are piston pumps. These are, like in your refrigerator. They help pump coolant and things like that when it goes through. So this is what a reciprocating pump is doing, all right? We just have a piston here, sucks fluid in, kicks fluid out, sucks fluid in, kicks fluid out, sucks fluid in, kicks fluid out. It just goes over and over and over and over, Kind of like, what a train track thing looks like as well, that go on the wheels of old school kind of engines and things like that, your steam engines that you used to see. Okay? So we have hydraulic pumps. They're either classified as fixed or variable delivery. So fixed delivery pumps have pumping chambers with a volume that cannot be changed. Okay, so those are kind of like our positive displacement pumps. Okay? In a variable design, chambers and geometry may change the flow, okay, allowing variable flow from the pump. So those are our non-positive displacement, okay? Fixed or variable delivery, essentially. Okay, another good cutaway here of a gear pump where you can literally see the gears in the middle, okay, and how fluid can come in and those gears rotate around, all right, and kick out, based on whatever velocity here. Piston pumps, if we're taking a look, all right, and this is one's going to be a little bit more rotary, right? We have it rotating around. Piston pumps may or may not be variable. This one probably will be a little bit because as it rotates around that larger chamber. If it's a simple like single reciprocating pump, not so much. Okay, we can kind of see what that looks like here on the inside. Try to find the pistons there on the inside of the diagram, kind of straight below the metal. But as those rotate, they're allowed to extend and retract. And you can kind of see as they slant up there through the cutaways. I should have one of these in class that I'll pass around for you as well so that you can kind of see. It's actually out of a vehicle, but it's out of a Dodge Ram, I think. I had a student that donated it to us. So. All right, so variable displacement pumps, okay, as this works. Okay, you can see what we have here, and this is the one I'm going to pass around in class, so I'll talk about a little bit more. But we have a swash plate here on here. So as that plate rotates around, it pushes pistons in and sucks pistons out, all right? So you have a bunch of cylinders in there, and as it rotates around, it's extending and retracting the pistons. Okay, as it rotates, it pushes one side in, and as it rotates around the other side, it lets the other side out. So the reciprocating end, okay, is on that swash plate as it kind of rotates around on the motor. It's very kind of cool to see. So I don't remember if this video was very good. Hold on, let me go back a slide and get this video to work for you here. It's obviously not going to work when I'm doing a recording session, so we're going to have to, let me try one more time and see if, there we go. I had to find the mouse, so sorry about that. Let's see if it works. All right, there's where we got it. All right, just so you can see, you know, kind of what's going on the inside and how that's working and how those are pumping and doing that sort of thing. Okay, so just like with anything, you know, how do we select what we want, right? I talked a little bit before about, you know, sizing the right horsepower, things like that. But there's different factors when we want to select pumps, okay, and what we want for them. So things you need to consider: the system operating pressure, the flow rate, the cycle rate, how long you want it to last, right? If you're in a factory, you don't want that breaking down all the time if you're using it, okay? Environmental conditions, all right? Is the ambient temperature always going to be the same in the room, or is it going to be hotter in the summer, colder in the winter? Is it outside? Is it inside? All those different things that you need to take into account. And, you know, obviously cost. You get what you pay for, too, sometimes. So, all right. Let's break down gear pumps a little closer. All right, so I've shown you some pictures, but you can kind of see here, this is how the gear pump is working in the diagram. We have the inlet, the fluid is coming in, and we are rotating around. Okay, the gears are obviously connected to a motor, that sort of thing, so we can see the power input shaft, electric motors, rotating those gears around. Okay, and you use one gear to drive the other, so we learned about that in mechanical, or if you haven't yet, you're going to learn about that in mechanical. All right, where we have our driver and our driven gear and that sort of thing, okay? And then as those gears rotate around, they discharge the fluid through the output, okay? These are called positive displacement pumps because, remember, we're going to get constant flow. Nothing varies, okay, because the chamber size will always be the same, and they're fixed delivery. So remember, positive displacement and fixed delivery go together, just like non-positive and varying delivery go together, okay? But gear pumps, positive displacement, okay, and they're rotary units because we're rotating around, and we have internal, or what we call planetary gears, right? Okay, so you can kind of see a good, you know, give here of, you know, showing you what's going on as the fluid's coming in, as the gears are rotating around, okay, and they're combining that and increasing it, okay? So the unmeshing and the meshing, remember that's the mesh point on the gears that we talked about in mechanical class, or you will if you're going to get there. As the gears unmesh in the inlet area, low pressure causes the fluid to enter the pump. Then as the pump rotates around, fluid's carried to the pump around and then discharged, okay? And the meshing area on the other side is the discharge, okay? And the fluid is forced out, pumped into the system. So we use gear pumps when we want outputs from, you know, below 1 gallon per minute, so something, you know, slow, up to 150 gallons per minute. So that's kind of where we vary between when we want to choose gear pumps for our system, and any type of pressure rating up to 3,000 psi. Okay, vane pumps, they're positive displacement, okay, but they can be fixed or variable delivery. So remember, positive displacement, we're going to get the same output flow, but we can vary if we want to. Okay, we use them in industrial applications, and then it can range from up to 75 gallons per minute. Okay, maximum pressure of 2,000. So a little bit below what the gear pumps can offer to us. Okay, vane pumps consist of a slider rotor filled with movable vanes, and you'll kind of see, I have one of these where you can see the vanes drop out and they kind of push it around in like a sweeping motion. Okay, so the rotor's off-center in the ring, creates the pumping chamber, and that's what varies the volume as it rotates around. Okay, so as the chamber volume increases, pressure decreases, bringing fluid into the pump. okay, and it fills part of that chamber. And as the volume decreases, forces fluid out into the system, okay? So this is a picture of what the veins are doing and what they look like, okay? So they're on the left-hand side, they're the kind of the little yellow things. They drop down using centrifugal force, okay? So as we're rotating around on that rotor, okay, so as that's rotating and as the chamber opens up, the centrifugal force drops the veins out, and the veins capture the fluid and push it around and then discharge it out the other side, and then the veins collapse back in and go out. So you can kind of see in the other picture on the right-hand side where the veins are, the ones that are up and the ones that are out. But it takes that centrifugal force as it rotates around, okay, it throws those veins in and out of the system to pump it around. Okay, so it's really kind of looking like this. So good little animation here so you can kind of see what happens to those veins. All right, we can clearly see the reds are the veins in there in the animation as they get longer and retract. Okay, and we suck the fluid around. So imagine the little white balls that you kind of see going around here. That's just, hydraulic fluid or oil that's going around. Okay, just so you can simulate exactly what's going on here. All right, so piston pumps. Positive displacement, fixed or varying, kind of just depends on how we have them set up, and provides high volumetric efficiency. So we use these for higher operating pressure, 10,000 psi or higher, and we can use them in high speed operations. Okay, so just a different way of how we look at some systems on there. Okay, and what they kind of look like if we're looking at just different pumps. So sorry, I flew through that slide. I want to step back here real quick. On the left-hand side, notice the symbol. It's just a pump, and I told you to know that from before. It's a hydraulic pump. Notice the symbol on the right, however, has a line through it. It means it's a variable system. Okay, so that's the difference between the two pump systems, right? The circle with the filled-in triangle. The triangle is filled in because we know it's hydraulics, okay? The line with the arrow means it's varying. Okay, so that's kind of how we can see on a schematic if we're looking at that. Okay, but going through the piston pumps again. Okay, and I've already shown you some animations. We'll probably see some more here. All right, but it's a pumping mechanism, and it extends and retracts, and I'll show you the cylinder in class. All right, as we, extend, retract, we're filling up the chamber and then exhausting everything out of the chamber. Okay, and if we have the other ones, I'm going to pass around the swash plate so you can kind of see that design, as it rotates around. And we've talked about this one already a little bit here. But if we talk about axial or inline, okay, pistons, okay, as they extend and retract, or if we have what we call a bent axis. So you can kind of see at the bottom as the pistons extend and retract, kind of like, using the swash plate or things like that as it goes through. But if we take a look here as it rotates around, and you can see how that swash plate rotates and moves in and out. I tried to show you this, before on one as well, how it makes everything pump in and out as it goes around. Okay? So remember they're radial, so I'm skipping over this slide a little bit, same kind of concept of stuff we've already talked about. So as we can talk about this and see how everything rotates around here, you can see where the pistons are and how they extend and retract, where the inlet port is and the outlet port, and how they kind of all work together to push everything through the system. So this is what it's really looking like in a radial system here. Okay, so as that rotor is rotating around in the system, we're sucking fluid in. Notice that there's balls and poppets, the little black circles on there that control whether the fluid is coming into the cylinder or out of the cylinder. And as we're sucking fluid in through the inlet, okay, and we're blasting it out the output or the outlet. Okay, so this is really what's going on when we have a radial piston pump going on. So this is a really good animation for you guys to see what's going on. Okay, and then on the right-hand side, we have the reciprocating piece. We're using the swash plate. Okay, and as the swash plate, it's tough to see on here, but that swash plate is really rotating in a circular motion. You can kind of tell by if you look at the key on the shaft on the left-hand side of it, you can see that that's rotating around. But as that rotates, remember that we're extending and retracting that piston in order to pump fluid through the system. Okay, we also have screw pumps. Okay, they have pumping inlets that consist of 1, 2, or 3 rotating screws, literally just like, a screw we put into wood. We have those threads, and those threads on the screw trap the fluid and push everything along. Okay, we use screw pumps when we want very low noise level going through a system. Okay, so notice that we have the inlet ports down at the bottom, and we use the screws to send it through. It goes through the threads of the screw pump and goes through the outlet. So there's a good kind of animation for you of what a screw pump looks like. All right, just remember that they're for operating at lower and quieter noise levels and things like that. Okay, just another picture, vane pump, and what the symbol looks like. All right, where we have the pump. And what I want you to look at is the symbol here, right? It's a hydraulic pump. It's got a line through it, so it's variable. Okay, and then look at the other. We have kind of a curved line with an arrow on it. That tells us the direction of rotation. And then it says that we have a separate case drain there that's located. Okay, so just kind of know all the different parts and pieces. And I want you to be able to recognize that this is a vane pump, okay, versus like a piston pump, versus a gear pump, versus a screw pump. You could know what all those sizes are. Okay, we might have a dual pump design, okay, where it's doing multiple things at once. Okay, so I'll step back just so you can kind of see dual gears on this pump, right? But what are we really looking for? Different symbols. So you need to know all these different symbols on your test. Okay, so I've already talked about indicating the pump, indicating the direction of rotation. Okay, we can see where the arrows are located. I'm looking at the second one where it says bidirectional flow. Okay, we got fixed displacement. Bidirectional means that motor can rotate clockwise or counterclockwise in this case. Okay, and then we already talked about the unidirectional with the case drain. And then we can do bidirectional with a case drain. And you can kind of see, as we add through here, what a double pump looks like, what a triple pump looks like, all schematically as we go through all this. Okay, so this is just some recapping here. Okay, we already did this. Gallons per minute is displacement times RPM divided by 231. So just another example here for you to look at, as we recap the lecture here. The last couple things just want to talk about is cavitation and what that really is. Cavitation is caused when the inlet pressure drops below the vapor pressure of the fluid and we form bubbles. I want you to think about laminar versus turbulent, which we talked about in a previous lecture. Okay, this is where we're getting turbulent fluid in the system. Okay, so that reduces the lubricity of the system fluid. Okay, and those collapsing bubbles can actually be very detrimental to the system and creates shocks. So this is like a damaged part due to cavitation. All right, so just make sure that you know that it's very important that we try and make sure that we have laminar flow inside our lines because it can do a lot of damage to all the components in our system. Okay, they're also noisy in pump operation, but the main focus is they do a lot of damage to the system. Okay, so just kind of see what the air clouds do to the impeller and different things like this. This is taking a look at what happened to it, kind of under an X-ray type scanner scenario there. Okay, we also have entrained air, okay, air that we suspend in the fluid. Think about like a bubble in a thermometer or something like that, or a bubble in a level. That's kind of the same kind of concept there. Entrained air, it enters the inlet line through leaks on the suction side of the pump or things like that. So I want you to think of what entrained air, think of like a level that we use in the mechanical class, right? And it's got that little bubble in the fluid. That's kind of like entrained air. It's trapped in the line, okay? Can also, cause different problems with the system, right? Think of like a blood clot in your system. It causes a heart attack or things like that, okay? It can produce similar results to cavitation, right? We might have laminar flow, but there might be a bubble in it or something. But it can still do a lot of different damage to the system and that sort of thing, okay? So just be careful. We always want to test inlet line pressure. It helps indicate what conditions existing. Okay, so high negative pressure indicates cavitation. Pressure closer to zero indicates that there might be entrained air, right, or an air bubble in the system. So just those two different things there. Okay. So The inlet line of the pump needs to be carefully sized and configured to eliminate cavitation and air entrapment. Okay, you don't want anything to be able to get inside there. Fluid velocity in line should not exceed 4 feet per second. All right, so that's another way we don't want to be able to. We want to make sure that we don't entrap air or create air pockets. Line should be no smaller than the diameter of the pump. Okay, this is just making sure that all the parts and pieces fit and put together. Strainer and inlet line filters must not restrict fluid flow as well. Okay, so lastly, last slide, part of the lecture here. All right, just to review. All right. Understanding pump flow rate. We've talked about this already, but just wanted to make sure I'm bringing those up for a reason. Make sure that they're in your notes and everything to take care of. Okay, so just recapping. Okay, we're talking about pump flow rate, those sort of things. We talked about gear pumps, piston pumps, screw pumps. All right, vane pumps, all those different kind of pumps and how they have a fixed or a varying, volume that they can kick out of there. All right, so remember, positive pumps output a constant flow versus non-positives can output varying flow and those sort of things. So that's the main concept, but know those main types of pumps. All right, and we talked about, when we might use them based on their PSI or those sort of things, or if they're loud or things like that. But, all right, guys. That's the end of Chapter 3. As usual, email me with any questions or else write them down and ask me when you get to class. We'll be doing labs on this stuff here. All right, so else, I'll see you guys in class. Have a great day.